So the last speaker of today is Pedro Salomão from SUSTech China, and his talk is about finite energy foliations in the restricted three-body problem.
So thank you very much for the invitation. I'm very glad to be back to this conference. In fact, I came to all of them, but the last one I was moving to SUSTech, was too far away, could not participate. So I'm very happy to be here again. Hopefully I will participate in the next editions. So I will, in fact, I will talk about finite energy foliations in the restricted three-body problem. It's a particular instance of the three-body problem. So I will quickly introduce this. It's, in fact, the circular planar restricted three-body problem. And I will quickly introduce this problem. So we have three point masses, let's say M3, M2, and M1, and they have position, let's say R3, R2, and R1 inside the space, and they are attracted by each other according to the usual law of gravitation by Newton. So we have these symmetric forces here between each other, and so the law of motion, let's say, let me write, so the position of this mass M3 is denoted by R3, and we have mass times acceleration is equal to the sum of the forces. So in this case, we have M3, R3, is going to be the sum of these two forces here, and we denote this by F23, F13, and so they are given by a constant that I will not consider here, and the product of the masses, so between here, so M2, M3, and then divided by the distance of R2 minus R3 cubed times this difference here plus the other force, which is the same idea, the force with M1. And then, of course, we have the equation for M2, the same thing, and M1. And the point is, so we have these three masses. In principle, they are positive. But if we look at this equation here, in fact, we studied the motion of the third mass. That's why I start with the third mass. So we see that M3 disappears from this equation here. And so we can think M3 as 0 if we desingularize this equation here by just eliminating M3. Okay? So, but if we consider M3 equal to 0, we see that this becomes a decoupled system. So it becomes essentially the equations of the two-body problem. And in this sense, so the problem is simplified. So restricted means we will consider like this limiting case of M3 equal to 0. Planar, so it's another simplification that we assume that instead of moving on the space, it's only on the plane, the motion of the three bodies here, and the circular, because the motion of these two bodies is ruled by two-body problem now with M3 equal to 0. So we assume that, let's say that this is the center of mass, that they are moving it, and this is a possible solution, they are moving along circular trajectories around the center of mass. Okay, one opposite to the other, and they move with the constant angular velocity. Here they just move with the constant velocity, okay? So this is essentially the circular part. And we study the motion of this body, which has mass 0, which we call the satellite, while these guys we call the primaries. Now we look at this equation, and this is, in fact, a complicated equation because now R1 and R2 are given functions that depend on time. But to simplify, we consider a system based on the center of mass that rotates together with these two bodies. So with respect to this system, these two bodies stay fixed. And we study the motion now of the satellite with respect to this rotating system. And this is essentially this Hamiltonian that we see here is the Hamiltonian that describes the motion of the satellite in this plane with respect to this rotating system. Okay, so Q is the position here on this plane. P is like the associated momentum, and there is a term here. So this is the kinetic term. Well, this is a magnetic term, and this is the potential associated to the other two bodies, now at position minus mu, and in fact, minus mu and 1 minus mu, and with the usual symplectic form, so we just have to integrate the usual Hamilton's equations associated with this Hamiltonian. So this is essentially how we get into this Hamiltonian. Just do this simplification in the three-body problem, and we consider this rotating system. We have that function which is preserved because now it does not depend on time. Okay? So this is a 2 degrees of freedom Hamiltonian system, and still extremely complicated. So let me say a few words about this system. So we have the two primaries at these points here. So mu is a parameter that we cannot eliminate from the system. It varies from 0 to 1. And the sum of the masses is normalized to be equal to 1. So it's the mass ratio between the primaries. And the system really depends on this quantity here. And we will eventually consider mu, this mass ratio, close to 1/2, like both primaries, more or less, they have the same mass. So, so the primaries are here, and that's the energy, and we study the motion on a fixed energy surface. So E is the energy, and if the energy is small, then the satellite can move only close to the. Let me just see the convention here, because so for mu, let's say that mu is small, then this guy is smaller than this guy. That's why I'm drawing like that. And so for low energy, the satellite moves here. let's say, well, it could even collide the primary, but it stays trapped around the primary. Or it could stay also here around the other primary with low energy. Or very far away, it doesn't matter. I will discard this component of the energy surface. But it's essentially a dynamics on this energy surface that because of these collisions, in fact, this energy surface is unbounded in the p direction. This is the q plane. So this is for low energy. If you increase the energy, like these regions, they start to become larger. This means that the satellite can move further, and eventually it hits a critical level of the energy. And this critical level of the energy, I will, these two regions here, they touch each other. We draw like that. And the satellite now has, so there is this unbounded region, it doesn't matter. So this is a critical energy equal to L1 that depends on mu, this first Lagrange value. And we have here a special point, which is a critical point of the Hamiltonian. And this is a saddle center equilibrium point. And the satellite still stays trapped in these regions here. There is a trajectory which stays fixed at this point. This is the projection. And you can also find like a trajectory going, converging to this point and leaving like the same thing on the other side. And don't know exactly how they project here, but it's just an idea that is a trajectory that converges to this equilibrium, and another one that converges backward in time, the same on the other side. But you cannot move to the other side, okay? So this is for E less than L1 of mu. And if you increase a little bit more the energy, then the satellite has more freedom. And now we have something. So here is this equilibrium point. We have something, the projection looks like that. And now it's like these two components, they were merged like a connected sum of three manifolds. And here I must say something. So we are, in fact, studying the motion of the satellite for this type of energy. Is slightly above the first Lagrange value. So it's bigger than L1, but at the same time it's less than L2. In fact, very close to this one here. So I mentioned, so we have these collision orbits to the primaries, and there are many different ways of regularizing this trajectory. So this trajectory is, if you have a trajectory which is very close to a collision orbit, so it more or less, it passes close to the primary and bounces back almost like an elastic shock. So there is a way to deal with this situation here. And one of the ways of regularizing these collisions in such a way that now a collision, you obtain a smooth map on a compact manifold, including these collision orbits, is using elliptic coordinates. So these elliptic coordinates it's given by this expression, and we change P and Q to new coordinates, y and x. X would be like the new position. And the relation between Q and x is given by those expressions involving hyperbolic cosine, hyperbolic sine, cosine and sine. And these coordinates, in fact, if you fix, let's say, cosine, you see x2 is like an angle. So if you fix x1, let's say, and this gives you, and you vary x2, you obtain like an ellipse. So, and the primaries are foci of the ellipse. And so these ellipses degenerate on this line here. And if you, so this is like how this x2 coordinate behaves. And you could do something similar if you fix x2 and you vary x1, then you have a family of hyperbole like, let's say, yeah, like this. And this hyperbola, they will eventually degenerate here in this way. So we change coordinates in such a way that the p dq is equal to y dx. In fact, it's more than symplectic. And we obtain these equations relating these coordinates, p, q, and yx. And then we consider the Hamiltonian in these new coordinates after regularization. It's necessary to reparameterize time. And there is this usual trick of multiplying the new Hamiltonian in the new coordinates by this expression here, which represents a reparameterization in time. And we obtain this potential here. It's the new potential. And this new potential is smooth. There are no singularities. And it's given by this term that includes the magnetic term here, plus a potential. And the potential we split in two pieces as the sum of these two terms here. And we immediately see that if mu is equal to 1/2, it simplifies a lot. Okay? That's one of the reasons we consider mu equal to 1/2, and not only that, a mu close to 1/2. So it's given by this expression here. So there are no singularities. We study the motion of this Hamiltonian here. Okay? So what we want to do is to study the dynamics for energies slightly above the first Lagrange value in terms of foliations using holomorphic curves. So so I mentioned, like, for low energy, so this is essentially the case studied by Poincaré. He studied in this low energy component after regularization, and the Poincaré found for mu very close to 0, close to the heavy primary, he found this annulus-like global surface of section. In fact, this is one of the reasons this problem is so important. It's eventually, so his studies led to the Poincaré-Birkhoff theorem. So this first return map to the annulus has a twist. Eventually, they got a generalization, this Poincaré-Birkhoff theorem for twist maps on the annulus. Eventually, Arnold conjecture, Floor homology, and so on. But for higher energies, we have the following. So in the case, even for lower energies, we have in in this situation here, 3 very special periodic orbits. These are the retrograde orbits around the primaries. So this is before the regularization. It's easier to draw these orbits. They are just like a simple closed curve around the primary. It's not a, but it's just a simple closed curve around each primary. And there is another special periodic orbit here called the Lyapunov orbit with a very small action. And this is hyperbolic, for sure. In terms of Collins-Ender index, it has index 2. Okay, while these ones, they have index, well, larger. So these 3 different periodic orbits, they, for low energy, we also have this guy here, this retrograde orbit. And so Birkhoff proved the existence of this orbit. In fact, this is proved by Birkhoff, and he conjectured that this orbit emits not the orbit itself, because this orbit is not contractible. So the double cover of this orbit inside the regularized energy surface, it bounds a disk-like global surface of section. And so when you, so both sides, in fact, the conjecture, both sides that the double cover of this retrograde orbit bounds a global surface of section, a disk-like global surface of section. But when you go above, this is not possible because you have these trajectories passing through one side and the other. These are unlinked orbits. And so what you expect in this situation is a foliation that emits these 3 orbits as binding orbits. That's the idea. So when we regularize so the picture that we have when we regularize, I will put x2 here and x1, is something that, so this is the critical set. So remember, x2 is periodic of period 2 pi. And if we consider like this interval here, the projection of the critical set will be something that looks like this. In fact, this regularization, in fact, is this double covering those coordinates. So, in fact, we have this point here. We should identify the antipodal points. These 2 points correspond to this singularity here when we go back to this. So we are lifting, in fact, under a double covering map. And we have, this is like the component, maybe this one. And there is the other component that looks very similar. And for mu equal 2.5, in fact, it looks exactly the same, the dynamics. There is an extra symmetry, and it looks exactly the same. So this is one component. This is the other component under this double covering map. But now the flow is smooth. It's a compact subset of the energy surface. So, if you are slightly above, what we have is something, the projection of the energy surface to these coordinates is given by this expression. So the Hill region, which is the projection of the energy surface, is just something that looks like this. And so this is periodic. So this should be like identified with this guy. This coordinate x2 is periodic. And in fact, what we see here from this projection is that the energy surface, well, it has regularized collisions with both primaries at the same time. So what we see is each slice here is like an S2. And because it's periodic, this component of the energy surface is S1 cross S2, which double covers, I will denote by RP3. So connected sum with RP3. So it's like for low energies, the regularized energy surface is S3 divided by 2 because you have this double covering map, so it's RP3. And then when you cross this critical value, it becomes the connected sum of this. So it's very important that up to this value here, up to slightly above the first Lagrange value, this energy surface that I'm projecting here, they have contact type. So you have this Liouville vector field, which is transverse. And so the Hamiltonian flow is equivalent to a Hebb flow. It's crucial to apply the symplectic methods, in particular to use the theory of holomorphic curves in symplectizations to study the dynamics restricted to this energy surface. So, okay, so there is I mentioned that, so Birkhoff proved the existence of these retrograde orbits. And in fact, it's possible to prove up to slightly above the existence of these orbits, and something slightly stronger that you can find like a local family of retrograde orbits. Like you fix a parameter and the energy, and locally you have like a family of retrograde orbits. So we consider here the space of parameters is in fact the mass ratio, which lies in between 0 and 1, and the energy for each mu you have this value, the first Lagrange value, and we will consider in fact values very close to 1/2. So so as I mentioned, we want to find these foliations of the energy surface that somehow generalize the notion of open books. So, and this idea goes back to Hofer, Vysotsky, and Zehnder. Alberto mentioned yesterday these open books on dynamically convex hypersurfaces in R4. So I will also mention, so these two results, the first one is the same Alberto mentioned. It's a more general class of Hebb flows on the Tightry sphere, assuming that all indices of the periodic orbits are at least 3. You have this open book. And, but if you don't have this condition, and if the contact form is non-degenerate, meaning that all periodic orbits are non-degenerate, then we have this finite energy foliation. It's a foliation in the symplectization, which is invariant under dr translation. And when you project this foliation in the symplectization to the trimanifold, you have what we call transverse foliation. You have finitely many periodic orbits with index 1, 2, and 3. They are all embedded. And in the complement of these periodic orbits, you have a foliation. And the leaves, they all have genus 0. And in fact, we will consider the case where we don't have index 1, just to simplify. And so in fact, in all the applications we have, we only see index 2 orbits. We never see index 1 orbit. So I will focus on this case. Then this finite energy foliation could have these binding orbits of index 2 and 3. And one of the particular foliations that we might see on the trisphere is this case when you have this. This is a cross-section of this foliation, this index 2 orbit. And this index 2 orbit has a pair of planes, an index 3 orbit. So you see this like rotating around this axis here. So this is the same orbit, this is the same orbit, and we have like a family of planes foliating the interior of this ball. This is the interior of a ball. We have a cylinder connecting the index 3 to the index 2, and this family of planes converging to the index 3 orbit. And outside is another ball. You can imagine the same foliation outside, the same cylinder here, and the same family of planes. So this is the foliation that we call 3-2-3 foliation, and it's obtained in the case, for instance, the flow is weakly convex, like no orbit with index 1, with some, and it's non-degenerate is also important. And let's say that this foliation is not the usual open book. We could create examples that we don't have the open book. So we would see a foliation like that, describing, giving a global structure of the flow. So, so this is what we mean by a transverse foliation. And so the result with Lei-Liu says that if we take mu sufficiently close to 1/2 and energy is slightly above this number, which is in this case -2, here for this space of parameters above the first Lagrange value, so we have a situation like that, we have a foliation that looks like this one on the trisphere, exactly the one found by Hofer, Vysotsky, and Zehnder, but adapted to the topology of the problem here, which is RP3 connected sum RP3. So the foliation looks like this, but we should see this in RP3 connected sum RP3. So this family of planes, they are not converging to an embedded orbit because the topology is different in RP3. In fact, it's converging to the double cover. It's like we take the trisphere to RP3 and we kind of see this type of open book in the case, in the dynamically convex case, but here we should see as each plane approaching this double cover of the heterograde orbit. So these two heterograde orbits and the Lyapunov orbit in the neck region, they have this foliation. So that's the result above the first Lagrange value. And one of the implications is, it's like if you intersect the, let's say, the unstable manifold of the Lyapunov orbit with a leaf, a local leaf of this foliation, it will be like a circle bounding a disk, and you use the foliation to flow this disk, and because you don't have too many possibilities when you have this foliation. Either you follow this foliation, either this disk, when you flow, will hit the disk associated to the stable manifold, and then you produce a homoclinic, or again, you will hit that same disk from the beginning on another disk, and you keep doing the same because you have a finite area of this. Each one of these disks is just the action of the heterograde orbit. Eventually, you have to, this unstable manifold has to hit the stable manifold of the Lyapunov orbit. So in fact, you always have infinitely many homoclinics. In both sides, you can use the argument on the other side and produce infinitely many homoclinics on the other side. And also, you can use this foliation to prove the existence of infinitely many periodic orbits, exploiting the fact that the flow is real analytic. So this foliation you might see as a global structure of the flow, because the trajectories, you don't have many possibilities in the sense that either they keep rotating around one of the retrograde orbits, it can, for instance, converge to the Lyapunov orbit if it's in the stable manifold, or it could pass to the other side. It's like the transit trajectories, it goes to the other side. And when it gets to the other side, it starts rotating around the other retrograde orbit, and essentially that's what it can happen with all the trajectories. It could now converge to the Lyapunov orbit through the other side, or go back to the other component, and so on. So you don't have many possibilities for the flow. It organizes in a kind of simple way. So there was this, I mentioned this conjecture by Birkhoff, which says that the double cover of the retrograde orbit bounds a disk-like global surface of section. So we prove also close to 1/2 that there is an interval here, an interval around 1/2, such that for every energy below this critical value here, the double cover of the retrograde orbit bounds this global surface of section. This was because Birkhoff proved the existence of this retrograde orbit, which moves opposite to that rotating system, but could not prove that there exists a direct orbit moving in the same direction of the rotating system. And so his idea, if you find this global surface of section, then there is a fixed point. This fixed point somehow corresponds to the direct orbit, which is an orbit linked. So because everything is abstract here, we don't know if the projection of this fixed point, this orbit corresponds to the fixed point, projects as a direct orbit, but Otto van Coort has some numerical proofs that for certain ranges of parameters, it really gives the direct orbit that it's still an open problem in the general in this general region. So now using some results with Umberto and in fact, this is proved using results of Umberto together with Umberto, and there is this another application that if you take this fixed point, this orbit, and the retrograde and the direct, they bound like an annulus-like global surface of section, exactly as the system that was studied by Poincaré for mu very close to 0, like in this region, because the flow is integrable, then the arguments by Poincaré are perturbative. But here, the situation is very far from an integrable system. So, but how do we prove the existence of this foliation? And, so there is, in fact, a small bridge between these methods in symplectic dynamics and these concrete systems. And one of these bridges is the convexity of the energy surface. So in this case, for instance, if you know, it's like if this is the projection for low energies, like the projection is like a disk a disk here. It's a three-sphere. So when you take the antipodal map, it's RP3. If you prove that these guys are convex, then you know about the indices of the periodic orbits, and then these holomorphic curves behave well. You can produce foliation out of this. So to prove, because we have this above the energy, above this critical level, we have this index 2 orbit. It's not dynamically convex anymore. But what we do to study above, we look at the critical level, which is here. The projection of the critical level is here. And this is the projection. And what we do is we prove that this is strictly convex. Okay? So this compact subset of the critical level, which is like a three-sphere but with two singularities, it is strictly convex. And above, it's also strictly convex, using elliptic coordinates. In fact, if you try to use Levi-Civita coordinates, the usual coordinates used to regularize those collisions, it's not strictly convex. You lose a little bit. And once you lose a little bit, then you don't have those estimates. You cannot produce this foliation. You have to use another method. But using elliptic coordinates, we can show that this up to the critical level, this hypersurface has, it's strictly convex. So what's the meaning of strictly convex? So it's like a three-sphere inside R4. Well, below you don't have singularities, but at the critical level you have like two singularities, and at the regular points all sectional curvatures are positive. So if you wish, we have it's embedded inside R4. You have the principal curvatures, and all of them have the same sign. We can choose them to be positive. So we have to check that. Let's say all the principal curvatures are positive. So what we do is we look at the Hessian of the Hamiltonian restricted to the tangent space of the energy surface, and we prove that it's positive, definite. So locally, you have a positive curvature. And it's not so difficult to pass from local to global to show that this positivity of the curvature implies that it's strictly convex in the sense that it bounds a convex set, and every hyperplane tangent to this level has contact of order 1. So, any questions? So this is essentially the main argument in this proof. We show that this is strictly convex, and what are the implications of this for the index estimate? So first we have this index 2 orbit, which is the Lyapunov orbit, and we show that there is no other orbit with index less than 3. So it's it's what we call weakly convex, but there is only one orbit with index 2. All the other orbits have index at least 3. So this is one of the consequences. But there is a very crucial estimate here in the proof. Is this region here close to the critical, to this critical point, is a region where, so it's like every periodic orbit touching a small neighborhood implies that this orbit has very high index. So let me explain this type of estimate. We can find like a neighborhood. You give any number, and you find a neighborhood of this equilibrium point, such that any periodic orbit passing or crossing, intersecting that small neighborhood has index at least that given number. So it could be very high. So it's like the closer you are to this guy here, the higher the index. And this implies some control on the compactness of holomorphic curves. So there is also an estimate which is intrinsic of this type of system is because it's like you choose a trivialization and you look at the linearized flow. When you get close to this point here, the linearized flow kind of, because it's a saddle center, the center part dominates the saddle part, and the flow starts to rotate. The orbits start to rotate around each other. This makes the index very, very large. And with respect to this trivialization, it's in fact a suitable trivialization. Once the index gets very large, it cannot go down after it crosses this region here. There is a kind of, it's typical for geodesic flows or potential systems, you have something very similar to this. Once you gain the index, you cannot lose anymore. And for this type of system, even with the magnetic term, it still behaves like that. So we can completely control the indices of the orbits, and this implies control on the compactness of holomorphic curves. So let me try to explain a little bit of, so it's essentially the construction of this structure here. And this pair of planes, so we have the Lyapunov orbit. This pair of planes, in fact, it lies in this small region here. It's like it's just a pair, it's a two sphere separating this region. It's very small with very low action. And you construct, exploring the quadratic part of this Hamiltonian at this point here. You rescale in a suitable way, and you find in the limit like quadratic part of the Hamiltonian. And this quadratic part has a lot of symmetry, and you solve for a suitable choice of J. You solve the equation, this PDE of holomorphic curves, by changing from a PDE to an ODE. Because it has a lot of symmetry, this is a usual trick. So then we obtain this pair of planes here, and this region now, in fact, this pair of planes is in a small region here. It gets closer and closer. We choose a family because this pair of planes is automatically transverse. So when we perturb it from the quadratic part to the whole part, they survive. It's like the Lyapunov orbits proved to exist. It's just an implicit function theorem, and these planes, this pair of planes, they also survive because they are automatically transverse. And then there is the construction. So this is like holomorphic curves in symplectizations, just basic definitions. And so for this family of planes here, it's a bit more complicated. So we would like to find this family of holomorphic planes asymptotic to the retrograde orbit. We start with, this is also the trick that Hofer used to prove the Weinstein conjecture for over-twisted contact structures on contact tree manifolds. We take the retrograde orbit and we take an arbitrary disk, and we look at the characteristic foliation, and we perturb, and the characteristic foliation is, the intersection of the contact structure with this plane. Except here that it's tangent, like the contact structure is tangent, and here the contact structure is transverse to the disk. We start with a disk like that. It's always possible to use a procedure of elimination of the singularities. And then the trick is to solve locally here and find a family of holomorphic disks. And these holomorphic disks, they lie in a one-parameter family of disks that do not intersect each other in the symplectization. In the projection, they might intersect. And the ideal situation is when this family of holomorphic disks, they reach the boundary and then they produce a plane like that. Well, in general, they will not, if they approach the boundary, this family here, they could produce a plane here. Well, because now we just have one orbit with index 2. Let's say this is the pair of planes that we have. So this family, well, it could hit and produce a plane, but it could hit and produce like a cylinder connecting this retrograde orbit to the Lyapunov orbit. But and then you know, the SFT limit includes one of these planes here. But the main problem, and this is where we have more difficulties, is when this family of planes gets stuck. So it might break, for instance, on something that looks like a half cylinder plus a plane, and then so fortunately we have this pair of planes. So if this happens here, our disks, they break like that, we may eventually glue them to produce a new disk, and with some uniqueness of holomorphic disks by Abbas-Hofer, we can show that this new family, after gluing it with the opposite plane, the boundary stays outside and the family continues. And of course, it might break again and again, but for generic J, you can break at most incountably many such half cylinders, and eventually we get a sequence of holomorphic disks approaching the boundary, and it will produce leaves of this foliation, and we can produce all the other leaves of this foliation out of gluing, compactness, and Fredholm theory. So this is the main argument. We need the usual trick, like you perturb the contact form, so it's non-degenerate up to a certain value of the action, and then we perturb J in such a way that certain holomorphic curves are generic, and we have this construction, and then we take the limit with the sequence of non-degenerate contact forms converging to the original one, and understanding the behavior of these leaves at the boundary, we know that this is stable and it converges to a foliation to the possibly degenerate situation that we have. So this is the usual construction. I still have 2 minutes, okay? So then, so there is this question of well, it's very technical, in fact, to prove the convexity. We have to prove that everywhere you have this positive curvature. If you go to Mathematica, you obtain like a big expression. It's easy to give up. Then it becomes a problem that you have to carefully manipulate all these terms and organize them in such a way that you can estimate each one of them and prove that each one of them is positive. So there are many steps. Let me just mention here that, so this is like 1/4 of this set that we see here. And the problems we have in general are concentrated near the singularity where the hypersurface is almost like a cone. The curvature goes to 0 there. So there are many estimates where we can reduce the region where we need to prove the positivity, and there are many tricks to replace functions that depend on this 3-dimensional manifold by functions that depend only on one variable, and eventually we show the convexity not only in this region but close to the singularity here. Okay, so I will stop here. Thank you.